The story of Croatian car company Rimac it's got elements of a fairy tale. So there's this guy called Mate, and he really likes playing with cars. He really likes cars. He really likes drifting cars. And he builds this all-electric BMW drifter that absolutely obliterates the competition, and at a very young age attracts so much attention from the rest of the industry. And I have been covering this industry for 20 years, so I have watched as Rimac has gone from being a guy in his garage to a multinational firm with a €1 million+ hypercar that if you have the money, it will make and sell you. But Rimac is not just a bespoke luxury automaker. It now is a majority owner of Bugatti. It now has a company called Rimac Technology, and I'm here at IAA 2025 talking with some of the team at Rimac Technology about the new, just announced solid-state battery development that Rimac Technology is pursuing. Daniel, you are the lead on this project. Tell us about, well, a little bit about how you got to this point and how Rimac Technology went from making the Rimac Nevera one of the coolest hypercars in the world to deciding to work in solid-state batteries.
Sure, I'll be more than happy to. So actually I joined the company roughly 10 years ago, and I've been working on all those crazy projects for other OEMs when we were building prototypes. We were building something for Jaguar, we were building something for Renault, so there were a lot of different projects there. And with those projects we kept learning more and more about battery technology. At some point Mate came with the idea that we should build a hypercar having all this knowledge inside of it, and that is how the Nevera was born, right? After that, we saw that our technology is not only suitable for us, that we actually can share that across the industry, and this is how we started to build Rimac Technology. So currently, we are in the phase where we are designing, producing, and delivering our current battery technology. And we are in parallel working on enhancements of that existing technology, but we are also trying to look further in the future. And further in the future are solid-state cells, right? So here we have an example of one battery pack that we are looking to deliver on the market sometimes in early 2030s. At that point, we plan to have fully developed battery architecture, scalable battery architecture, based on the solid-state cells that enhances and enables so many opportunities on the system-level design.
So right now, Rimac is working on an NCM traditional battery pack that you are working with customers across the industry on. And
Correct.
Today, you've just announced your intent to do the same thing with solid-state technology, but still using NCM chemistry, but with a very important difference, right?
Exactly. Up to now, we were using 2170 cells, 46 XX cells, so we had 46 cells with a different height for a different project. But now we are starting to work with solid-state, which at this point in time comes in a pouch format. And we plan to build or design our next generation battery packs based on that.
And tell me about some of the challenges working with solid-state technology.
Well, I would say if you ask a cell supplier, the challenge there is how to produce those cells at scale for some normal cost, cost that can be used, or the cells that cost at the level that can be justified to put in the battery for the vehicle. Yeah. The other challenges usually when you work with pouch are that you need to have some kind of a clamping element or effect on the cell in order that you apply pressure, because pouch cells don't usually work without applying pressure. We here work with Prologium and they are solving several key challenges already on the cell level. By not having to apply pressure here, we can have or we can achieve cell-to-pack architecture even with the pouch. As we speak now, I don't know of any other battery pack in the world that uses a pouch, cell, and achieving a cell-to-pack architecture.
Yeah, and you're leveraging Prologium as your cell partner and focusing on the actual pack manufacturing. You've got some other colleagues on the stand today who focus on your battery management, and other colleagues who are focusing on drivetrain power electronics. So that's really offering a fully finished package to OEMs that includes battery and drivetrain. Whatever they want, you can provide the engineering skills to get it through.
Exactly. I'm sure you'll see as you go through the booth that we are offering not only battery technology, but as you mentioned, everything actually that you need to build an electric vehicle, you can get it from us. When we talked about the cell itself, yes, we are now working with Prologium, but we are not limited to only one cell supplier. We are open to collaborate with everybody who actually are bringing benefits to the battery world. Yeah.
And through solid state technology, obviously you have electrochemical and mechanical stability that you don't have with current NCM technologies. Yeah. We were talking off camera earlier about charge rate, and you're targeting 6.5 minutes for 20 to 80% charge.
From 10 to 80%.
10 to 80% charge. And that is a very impressive time that brings yet another one of the challenges of EVs to the fore, namely recharge time.
Yep.
And that last 20, 30% of drivers who won't switch until they can recharge as quickly as they can fill up with gasoline or diesel. Do you think that in the future this kind of recharge time is going to become the standard expectation across the board?
Well, definitely. Every user wants to charge quicker, right? I would say that yes, we will need to allow users to charge quickly, but it's not going to be like every day. When you travel maybe between the towns, then yes, we will need to enable this fast charging. And I think yes, every vehicle on the upper end of the range will need to be able to charge quickly.
And one of the things you were telling me earlier is that instead of using a water-based cooling system, which is what you use in NCM, you've designed a new cooling system for use in solid state.
Well, these cells enables additional feature, and that is they act really well on the lower temperatures. So at -20, they keep more than 95% of energy. With that, we don't have to heat them up. They operate quite well on low temperature. We don't need to heat them up. Therefore, we can use the refrigerant as a coolant inside of the battery pack. And this is what actually we are using here. Using the refrigerant inside of the battery pack enables again some optimization, better like enhancements on the vehicle system design or vehicle system architecture. And there you can, for example, now eliminate coolant pump for the water glycol cooling. You can eliminate the heat exchanger, and you can actually, of course, yes, increased in power. You can use the same AC compressor for having cooling down the cabin and for cooling down the battery pack.
Fantastic. It's been so interesting to chat about battery technologies. Thank you so much. I'm going to tour the rest of your booth and see what some of your other colleagues at Rimac Technology have been working on.
It was my pleasure talking to you.
Thank you. Moving around Rimac Technology's booth a little bit further, we come to the inverter and motor technology, and Vardan here is going to tell me a little bit about what makes the technology that Rimac Technologies have developed so special. Now, Vardan, I've been following Rimac for a long time, you're no stranger to producing really high output motors, really high output power electronics. Obviously in the Nevera, ridiculous amounts of power that it can put to the wheels. And that's giving you all a really good starting point for developing inverter technology for other customers, right?
Yeah. So just, as you mentioned correctly, so basically that's what we did. We did Nevera, we took the Nevera as the foundation, and from there on we evolved the technology and pushed it even further. So if you look at the Nevera rear axle, just for an example, it's around 1 megawatt of power, around 10,500 newton meters of torque, and it weighs around 198 kilograms.
Right.
So that was the previous gen. And the inverter there itself is around 40 kilograms. And here, what you are seeing here is our latest generation inverter, but this is just an A sample. The B sample itself is almost, let's say, 60% of the size further.
Right.
So this inverter capable of same power, same currents, similar, let's say, backgrounds in terms of 6 switches, and this is a dual inverter, so it can control 2 motors in parallel independently.
Right.
And this can do up to 800 kilowatts and only weighs 11.5 kilograms in series. So you see going from 40 kilograms to 11.5 kilograms. It's up to 925 volts.
Right.
We have, in the single inverter, we have a 400 volt version as well, but we preferably try to work with the 800 volt architectures. We think we can bring out the best efficiency in that
Right,
subject.
more efficient, higher voltage, less current,
Exactly.
which means that you can miniaturize components more. Now, I'm looking at this. This is all silicon carbide technology. Obviously, if you've been following the EV world for a while, you might have heard of the transition away from old IGBT transistors into silicon carbide technology. For those who haven't, though, just give me a 20,000-foot view about what makes silicon carbide so revolutionary in the inverter world.
Again, if you go back to our previous generation, that was an IGBT-based inverter. So you see, in terms of the efficiency and in terms of the switching itself, so this inverter or the silicon carbide, the gate drivers, how it combines with the gate drivers with the embedded hardware, and the chips itself can help accelerate the switching process much faster. So it's much more efficient. You require a lot less cooling. It can be very compact, so it requires a lot less space, and it's then the current capacity or the let's say the current arms capacity or the density of the current density basically per power module as compared to an IGBT is almost 3 to 4 times.
Right.
And this goes on, again the efficiency increases, so an IGBT module would be in the range of 97 to 98% efficient in terms of the inverter at peak, and this one is up to 99.5% efficient in terms of the peak. So this helps in every manner of the way.
And of course, if you're switching more quickly, that means you actually can offer a more responsive driving feedback. You are more able to use built-in traction control, more responsive traction control, and just an overall more connected driving experience for the driver, right?
Yeah. So, using, let's say, now the hardware side or the power electronic side can switch very quickly. And then on top of that, what we build is our one board technology, which is our PCBA with the inbuilt MCU and everything else. And that helps us to go from, let's say, accelerate the switching and add all this software features on top of it. So everything is built in-house. So we have our normal, let's say, inverter functionality software based on AutoSAR. And then on top, we can add traction control, all the torque vectoring. So we can do torque vectoring, ELSD features, anti-jerk control, everything on the same PCBA. So everything is inbuilt into this.
And of course, if you're adding torque vectoring at the chip level, then you actually reduce the weight of the drivetrain as well, because you do away with all of the differential capabilities if you go for four-wheel drive, for example, or all motor. But you can also pull more technology and more tricks with the motor, right? If you're smarter here and you're quicker here, that means you can respond more quickly with the motor.
Yeah, I mean the latencies, so usually the traction control and this kind of vehicle dynamics things happen on the VCU or the PCU level. So then there is a layer from there coming to the inverter or to whatever the propulsion system is, and then it follows the lead. But here if you are enabling it directly on the inverter or on the motors directly, because both the motors are independently controlled, this is what gives us supreme control. So basically we are playing sub 5 millisecond per overall response
Which
rates.
is incredible.
Exactly.
Which is incredible. Tell me a little bit about the motor design as you've revised it now.
So the motor design, what we call is our HPM machine, which is a hybrid permanent magnet. I mean, that's a terminology, or let's say our trademark. So the technology itself is basically based on an IPM, which is we have, let's say, customized it, or we have done our novel magnet shaping to make it much more closer towards an SPM. So when you say IPM and SPM, so SPM is a surface permanent magnet machine, which can deliver a lot of torque, but there are consequences to that as well.
You have
So-
a higher back EMF, right?
Yes, you have a higher back EMF, which requires a lot of torque ripple to manage, which requires a bigger system to design to less efficiency, and the magnet content is higher, so it's much more costlier as well. On the other hand, an IPM is much more efficient, even on the lower operating points, has much less magnetic content, so it's cheaper, but it's not as torque dense as we would like it to be. So that's where we came up with something. We tried to take the best of both worlds,
and
we
combine.
combined it into an HPM machine.
And that results in lower back EMF, but higher torque.
Higher torque density, much less cost, much less magnet content as compared to an SPM, much less torque ripple, and much better efficiency.
And a higher rotational capacity as well, right? Higher speed.
In certain designs you can do that, but the rotational capacity is much more based upon, let's say, how you do the rotor design itself. So here also you can see, like, we have the bigger E-machine which can go up to 17,500 RPM, but the smaller E-machine with the lower diameter, without any carbon wrapping or anything, can go up to 24,000 RPM.
And this is something that Rimac Technology has taken from the Nevera and now can build this technology into really any kind of desired finished product in terms of 200 kilowatts at the wheels up to 1 megawatt, 2 megawatts.
Exactly. So that's the idea. I mean, we took the Nevera as more of a foundation, and now we are progressing this technology, going from there towards mass market.
Right.
And when we say mass market, our intent is still to be, let's say, focused on the performance variants of any car. So we are talking, you can take an Opel Astra and have an RS version of it, and you can use a Nevera axle.
Right.
So you can go from there, from any hot hatch to a sports coupe, like an Alpine, to a Porsche Taycan, or going up to a Macan or anything else in terms of our Lamborghini Urus. So you can see the whole range of our products, which is basically like building blocks. So we have a single inverter, dual inverter based on same technology, same architecture. We have the, let's say, our HPM machines, but only in different sizes. So we just change the diameter or axial length as needed. It's developed in the same manner. It's validated. It can be produced on the same line, and then we just change the gear ratio, and we have multiple applications. You can see it here as well. So here, if you see our dual axle at the back, that is intended, or that is going to be customer produced in around 10,000 units per year from next October onwards. And that has the same dual inverter which goes here, and the bigger E-machine.
And the dual inverter is what you see at the top there
Yes,
of the motor.
exactly.
So it mounts on top of the of the axle.
And then when we take the single inverter, the one of the motors, then we have the axle in the middle, which can do up to around 6,500 meters of torque, and can be a rear wheel axle of any of a performance sedan or a sports coupe. That's the requirement. Then we take the same single inverter, smaller motor. We have around 3,500 Newton meters of torque. Can be a front wheel application for any hot hatch or any car.
Right. It's always fun because I like to think of Rimac in some ways as like the Lotus of EVs. So you've taken a technology that you've become really proficient in. You've proven that you can do it through the Nevera, through a really high performance, desirable vehicle. And now you're going, hey, OEMs, wouldn't you like some of this?
Exactly.
And you can save them the engineering costs.
I mean, they don't, because the platform is already developed, it's already going into production, so they don't have to reinvest, they don't have to revalidate a lot of things. So for customer projects, we go directly from B sample to series, so it's much shorter time to integrate this as well. They get a much far superior product, let's say for their performance variants, where they also have a higher margin, and then we, with our software touches on top, we just can take it to a different level.
And I'm assuming that everything that you've got here can integrate with an OEM's BCM, other elements of the OEM systems.
Yeah, exactly. So our inverters, or let's say our communication, is very flexible. So it can go into any vehicle architecture. So we have CAN, FD, FlexRay, Ethernet. It can communicate in all senses of air. So basically our devices are much more, let's say, plug and play. So if the OEM wants us to add some of their custom application part onto it, that we can also do, or we can just use our layers and then provide them everything as we need.
Well done. It's been wonderful. Thank you so much.
Thank you.
I'm going to go and talk to your colleagues
Thank you.
in the battery management division. And finishing off my little tour of Rimac Technology, let's talk about battery management here with Christian. It's wonderful to see the progression that Rimac has gone through to bring battery management and power electronics into the next generation, based on all of the experiences that you've had with Nevera and with developing new platforms for OEMs to use. Tell me how you all went from the really, really high power electronics and battery management that you needed for Nevera, because the more you strain a battery, the better the battery management system has to be, right?
Yeah, exactly like that. So this is like our fifth generation of the BMS in the company. We are doing this for now almost more than 10 years, and we started with a little niche market, and now we are shipping it to the major OEMs. It's really incredible. And the main idea for us, 2 years ago, when we were doing this new BMS platform Gen 5, it was that put everything together in the one big project, put it all in the one big text, I would say, the requirements, and then from that we built the best BMS that we can. And basically the idea for that was that let's build it not only for the high performance, build it for the compact cars also, because we want to sell it not only for the for all the Bugattis, for all the Neveras. We would like to sell it to the compact cars, to bring this high performance to the compact segment of the market. It's not only high performance.
Exactly. So when you are building a modern BMS, it's no longer just, are the cells the right voltage?
Yeah.
It's, are the cells the right voltage? Is the cell at the right pressure? Is the cell at the right temperature? Are there any anomalies in resistance readings between the cells? It's super complex, right, to get a modern BMS reliably.
I would say with each generation there are much more parameters that you need to measure, and with that the system, as you said, becomes more and more complicated. Also the functional safety became more and more off the shelf. You need to have it. It's not and it's not anymore. It's going to the highest levels, and you need to have it on the really all the cars that you drive. So that's one of the.
And remote telematics become a thing. You're integrating with remote telematics for remote diagnostics. Have you done any work on twin modeling with AI or predictive battery management yet?
Yeah, basically we have in the company already this advanced SOX team where they are building these advanced algorithms where we actually put our BMS, and the software on its own learns from the pack, learns from the cells, from the insights of the cells, and can adapt to it and can actually efficiently manage the whole.
That means you can get more energy out of a battery pack, right? Because you understand when the cell voltage reaches this point, the battery really is not okay. Or maybe if the current stays below a certain threshold, maybe you have more power that you can give.
Actually, this is the important thing. So with each generation of the BMS, you have a better technology. You have a more accurate sensors. With that, you will get more power and more energy, and you will get more range at the end. So this is one of the things. And also with that, basically the cost with each generation is going down and down, and you're having a more affordable cars.
Now, Rimac Technology today announced that it's going to start working on solid-state battery technology. What are the challenges between working on, say, an NCM traditional electrolyte battery, shifting that to what you're working on, which is an NCM with solid state technology? What are the challenges switching from kind of a traditional cell design to a more futuristic setup?
Yeah, one of the things is actually the packaging itself, because you are changing the cells are now much bigger. All the pickup points, like the measurement points, everything is like much different. Also, there are some new things that are also coming in, like electric impedance spectroscopy, where you can actually measure the temperature inside the cells with advanced BMS. This is one of the things that we're like also trying to push in this solid state. But I would say the packaging, the whole new concept is like really a challenging thing.
And when people think about battery management, especially if they've been in the EV world a long time, they might think that, you know, oh, my battery management might measure in tens of volts or maybe millivolts. But the resolution that you have to work on for a high performance, long life battery pack, it's much finer detail than that, isn't it?
Now we are like going in 0 point something millivolts, 0.1 millivolts, and like we are going also in amp range, we are going to the much higher currents because the cars are much faster, so we are going in kiloamps. So also we need to measure this, also with the really high precision, because our current measurement today is 0.5% for the full scale. So it's something that really changed over the years.
And obviously as battery pack voltages go up, the range of current that you're using also changes. So instead of having a lower voltage, higher current pack, you're now switching to a higher voltage, lower current, which changes the characteristics again.
Yes, of course, changes that, but also the EDU suppliers are also like wanting to use more power, always more power, and the more power is the really pushing everything. So this is also something that we are also. And regarding this switch from 400 to 800, always this isolation things, this is the interesting thing and the like challenging.
Right, because the sense wires are very small.
Yeah.
And they don't actually carry a high amount of energy.
Yeah.
They're just really to sense. But then when you have smaller wires, then resistance becomes an issue that you have to factor in as well. And it's like a little dance, isn't it?
Yeah, so basically when you're going from 400 to 1000, it's a completely new game, because you're introducing like some parameters of the system that you even didn't know that exist, some capacitors, some resistances, and then all of these things matters, and we actually are really now pushing that we have a connected simulations and everything, because you need to all do in advance and then like execute later.
So what has been your favorite part of working on battery management at Rimac Technology?
I would say isolation measurement, because that's the most problematic thing, and basically with this like everything is going now hybrid, and this is like really a big issue, and everything is changing. In the hybrids you're always having these cycles all the time. The battery is going from the full to zero like really fast, and you need to measure this isolation, and this is one of like really key safety features that you
making sure there's no
false error.
False errors.
Yeah.
There's no electromagnetic gremlins in the system. It's been an absolute pleasure touring Rimac Technology. I hope that the company continues going from strength to strength. Thank you to you, and thanks to the rest of the team for giving me such a wonderful half hour or so tour of the booth. Thank you. So there you have it, guys. A fantastic tour of Rimac Technologies to finish out our IAA 2025 coverage here in Munich. It has been phenomenal. I make no bones about the fact that I'm not a fan of coming to auto shows. I'm not a fan of tech shows. I am an introvert. I don't like loud, noisy places. I'm neurospicy, and you know what? I'm just gonna say it. I think we did a really good job this year of covering the event. I know that there's a whole load of things we missed. If you haven't seen all of our videos, do go back and watch them again, because it's been fun to make, and hopefully we haven't taken too long to roll these videos out. Anyway, if you'd like to hear more from the channel, if you'd like to see what we do on a normal basis, which is more of car reviews, industry analysis, we do features, we do our weekend roundup show. You'll find it all on Transport Evolved. And if you like sillier stuff, then why not check out Transport Evolved Take 2 at the weekend, where I will generally show you my chickens in my garden and talk about a topic that's been bugging me. Anyway, hit subscribe. If you want to support us on Patreon, that is an option too. But from IAA Munich 2025, bye!
Thanks for watching us today. You can connect with us on Patreon, Discord, Mastodon, Blue Sky, or through our website. Huge thanks to the amazing folks scrolling by right now. You're the reason we can stay independent and keep making content without corporate influence. And right now is a perfect time to join. Through September and October, we're running our autumn Patreon drive. Sign up and you'll not only support the channel, but you'll also get an exclusive piece of digital art from Erin. Want to see your name here too? Support starts at just $1.50 US a month, and you can even gift memberships. And of course, a massive welcome to our newest members: NYTMR, Chris Wright, C&K Adventuring, Andy Pyatt, Gerald Eden, Kurlakos, Chip Chandler, Robert Nelson, 00 Critical, Tom Fagden, Barry 2379, Mike Coffeen, James River, Eric Knack, Hans Rose, DW, Merrill Fratkin, Kristen Rasmussen, MX Menivar Vargas, Stephen Nichols, Panther Legion, Kit Saprida, Bark Eater J, Jeff Good, Conrad Zalance, Frank Snyder, Jeffrey Smith, Tony Roberts, Matthew Frake, Jacqueline Cockburn, Fritz Coker, Trans-Vegan Cyclist, Jade Diaz, Laura Shear-Clark, Everett Garnett, Peter Broadwell, Jeremy Redmond, Patrick Matthias, Pamela Not Pam, Dave Fry, Mark Anderson, Tal Hobson, C. Daniel Tideman, Martin May, Fee, Donovan, Date Downs, Matthew Buckar, Zach C, Taraki, Kathy Windandy, Alex, Patricia Connor, Lindy Melendez, Dameron Can, Gary Robotham, Dave Miles, Tina Ponish, Mark Kruger, and Tyler Walker. Thank you all for joining in the last month. You're helping us hit our goal of growing Patreon support by 20 to 40% this autumn. Prefer a one-off contribution? We've got Ko-fi, Bitcoin, and a PO box, our swag store, and even an Amazon affiliate link, so your money helps us, not Jeff Bezos. We post new videos every few days on the main channel, plus extras on Transport Evolved Take 2. And since YouTube comments aren't safe for us anymore, the best way to chat is through Patreon, Mastodon, Blue Sky, or our website. If you want more, the algorithm thinks you'll like this video, but we'd love you to check this one out too. Be awesome, be kind, be intentional, and never forget to resist. Keep evolving.